All right, let's consider a brief history here of chemistry and what we know about chemistry. Because when you take a look at some of the names involved, we somehow think that chemistry developed in a vacuum in Europe sometime after the 1600s. So let's take a quick look at this. So we want to look at three different scientific laws, and we want to explain what they mean, and we want to look at Dalton's atomic theory and which parts of it are still working or appropriate today. So chemistry dates back to ancient times. We could look at it in terms of Greece. It certainly dates back to ancient Egypt. We use the term alchemy to discuss what was practiced in Europe during the Dark Ages. But that term actually comes from an Arabic term, which we'll see in a second. During the time when we did alchemy in Europe in the Middle Ages, we discovered a few elements, we made a few compounds, and we started to develop what we consider to be modern chemistry in the 18th century. But a little more history first. All right, so we use the term alchemy to describe what was going on in science in the Dark Ages, where we're looking at trying to take lead and turn it into gold and all sorts of scientifically pretty shaky things. But in fact, the term does not come from there. It comes from much, much earlier, and it comes from the Middle East. And we're looking at this, I'm not even going to try to pronounce his name, except for we're looking at here, Gerber or Gerberus, where he looked at how to do chemistry or science in terms of experimentation and laboratory. Now, it was perverted later on in the Middle Ages in Europe, but in fact, science or chemistry here could really be considered to be developed in the Middle East in the 8th century. All right, so we need to look at three different laws. We need to consider the law of the conservation of mass. Antoine Lavoisier proposed this, and what he said was anytime we have a chemical reaction, matter is neither created nor destroyed, which tells us that every little atom that we start with in a reaction is going to go somewhere. It's still there, it doesn't get changed into anything else, neither created nor destroyed. The law of definite proportions. The law of definite proportions says that if we have something like carbon monoxide, it is always going to contain a certain ratio, and they did these by mass. We didn't have a knowledge of really of atoms or moles then, but it contains a certain mass of carbon to a certain mass of oxygen for any time you make this compound. So in the case here of water, for example, we knew that water was always going to contain 2 grams of hydrogen for every 16 grams of oxygen, or if we look at the ratio, we are going to do 8 grams of oxygen to 1 gram of hydrogen anytime you take and make water. All right, that is the law of definite, consistent proportions, and we have got one more. All right, so the last one here is the law of multiple proportions. Law of multiple proportions takes the law of definite and just ups it one thing, because instead of having a solid, consistent compound, for example, H2O, we're going to say if we have a couple of elements that can make a series of compounds, so for example, H2O and H2O2, it's still compounds of hydrogen and oxygen, but we can have them in different ratios. Now, they're not the same compounds because the ratio is different. And what we're going to look at when we look at the law of multiple proportions is how they are different. All right, so let's look at an example of this. If we have CO and CO2, first of all, these are two elements and a series of compounds, meaning they have different ratios. And what they're saying is that the mass or the ratio of these masses can be reduced to small whole numbers. So if I have 16 grams of oxygen for here versus 12 grams of carbon, and in this case on carbon dioxide, I'm going to have 32 grams of oxygen for every 12 grams of carbon, what they recognized was that this ratio or this difference right here was a whole number. So that is our start on the law of multiple proportions. So let's look at these. Which of these represents the law of multiple proportions? Well, first of all, it has to be the same two elements. So therefore, not this one, or this one, or this one, because the elements are changing. It is only this one. All right, so let's put these three laws together. We have the law of conservation of mass, that mass does not change in a reaction, that is neither created nor destroyed. We have the law of definite proportion, which says that any compound is always going to be the same ratio by mass of elements. And then we have the law of multiple proportion, which tells us that if we have a series of compounds, that the ratios of the different elements are always going to be reduced to whole numbers, and whole numbers is very important. So Dalton put this all together and came up with this atomic theory. So in a nutshell, elements are made up of atoms. All right. Now, with the atoms, they had made an assumption right here, and that the atoms are indivisible. Next one, all the atoms of an element are identical, and that the atoms of one element are somehow different than atoms of another, which tells us that all oxygen is the same, but somehow hydrogen is not oxygen. All right. We don't know the details of why, but we know it's the case. Compounds are going to be made up of a fixed ratio of elements. So if we have a compound, for example, CO2, it's going to tell us that it is more than one type of element, and it's always in a fixed ratio. Now, we put this together using Lavoisier's theory of mass conservation, and we say that in a chemical reaction, atoms only rearrange. They're neither created nor destroyed. They simply rearrange and make new compounds. So that's where we stand right now, is that atoms are indivisible. All the atoms of a given element are the same. Compounds are two different elements in a fixed ratio. And in a chemical reaction, atoms just rearrange. They are not created or destroyed. And the interesting thing is, in fact, this mostly works today. The only thing that is different is that we know atoms are not indivisible. We have subatomic particles, and we know that each atom is not identical. We can have isotopes where we can have changes in the number of neutrons, but it will not change the chemical properties.